Okay. Okay. Oops. Let's see. I have a problem in mind here that we should be able to get to today. I hope we are not delayed. It is true that online I seem to take a little longer than in person. So hopefully we don't have to delay the exam. I don't think we will have to because we still have one more class next Monday. And then, so basically the exam, I said this last time, the exam is a week from today. So it's not, it's a week from today, it's not in the next. So I'm still, what I'm gonna do is I'll finish up everything in the next class. Now the idea is to have a little bit of time also for practice, the practice exam. Now, I'm not sure I'm going to be able to do the entire class practice exam, but it will be most of the class practice exam. I may have to finish up this capacitor stuff that we're discussing today. So on Monday, what we can do is if we don't have enough practice exam time, we can do office hours. I'll try to do as much practice exam time as possible. So that will just prevent us from delaying the exam. We want to take the exam a week from today. That really works nicely. So I'll have more instructions for you for the next class, more details about what could be in the exam, what could not be in the exam, what to expect, and so on. Now, today, need a little bit of coffee. Get myself a little bit pumped up today. We got to get through an example of, so again, this is an example that will show up in the exam. Let me put the chat up in case somebody has questions. If you have questions about the examples, now I haven't done capacitors yet. Luckily, capacitors is not something you need to talk about for a long time before you start to launch into examples. So definitely, we should have enough time. Now, the dielectric part of the exam, that's not of the class of this PowerPoint here. It says capacitance and dielectrics. I'll mention the dielectric thing, but it will be, I'll go pretty fast through that actually to save a little bit of time. And so, since I'm going to go through it pretty fast, I will emphasize it in the exam. So I may just have a very short question on something that I say very clearly. But don't worry about the dielectrics part so much. Okay, so don't think there is going to be a lot of that in the exam and that you need to cover it. Again, I will give you a lot of guidance about what to expect. So I already told you problems that are going to be there for sure. So you really want to focus on the things that I say for sure are going to be in there and not miss those points and worry a little less that maybe there was something that you have to cover that you forgot or something like that. That's not really going to be the bulk of the exam. Now, some people want A's, they want to get everything perfect. That in physics tends to be a little bit unrealistic. Almost everybody, even people who get A's, miss points. So, don't go in there thinking that you're going to ace absolutely everything. Just wait until you hear what the mean of the class was to figure out, oh, okay, I did okay. Or I don't, it's like half a curve. I do curve a little bit. I'm not going to, if it turns out that the exam is very hard, of course, then the curve helps you, because everybody went down in the grade. So of course, curve is not always a bad thing. Some people get a little frustrated with curves because it seems like you're competing with other students. It's kind of like half a curve, half not a curve. But definitely I do pay attention to the overall, how the class did overall. Otherwise, it would be impossible in physics to know. Because grades go up and down in physics a lot. So you got to curve a little bit. Sometimes that helps, sometimes it doesn't because the class did very well. Okay. But again, today I am going to give you another, so when I get to it, I'll give you an example of a bunch of capacitors in series, in parallel, this and that. And there will be a problem just like that in the exam. So you're not going to miss it. I'll tell you, this is something just like, it's not super easy though. At first, it seems that it's going to be a little easier than it turns out to be. Okay, so let's hope we can get to that and clear it up. And if it's not clear, ask me. And we made, some of you or many of you, I don't know how many, that's up to you. We could do office hours. So maybe some of you can stay after class today if you didn't understand what I was saying. about the capacitors or exactly how that works, or maybe you can do it after Monday, and then whatever you want. So if somebody stays after class today, then okay, so then we stay after class. That's a long class, so we probably don't want to do that all the time. That's kind of exhausting to do that very frequently because it's a long class and then office hours. But strategically before exams, I think it makes a lot of sense. So maybe on Monday you want to do that. It's up to you. Okay, so we'll see what happens with that today after class. But then Monday we will see again what happens. Okay, so again, please, if I go a little fast, that's just to save time for the part that I know you need to know for sure and give you time to digest that part. Okay, so allow me to go a little bit fast through certain parts of this PowerPoint to focus on what I know is in the exam. So I won't spend time on dielectrics. To begin with, I'll give you the practice problem before I even go into dielectrics. And then I'll wrap that up pretty quickly, either at the end of the day or maybe on Monday. Okay, what is a capacitor? Well, a capacitor, in essence, a capacitor is pretty short. It's pretty easy. It's something that holds a charge. Now, it turns out that the charge density, the energy density of a capacitor is not great. So that's why they don't use it for electric cars. But they use it, they're trying to tell you here that you do have it in your iPhone. The iPhone has a capacitor. So a capacitor is just two plates that hold a charge. Now, again, we should derive, most of the time when you say a capacitor, you're not gonna use something like this. The reason, let me just tell you briefly why this kind of capacitor is not the one that we're gonna be talking about. One of the reasons is very practical. If you were in industry, you would wanna know how much energy density, how much energy is this capacitor holding? Because what you really wanna know is, how much energy there is stored. So capacitors store energy. They don't dissipate energy. It's not like a resistor. A resistor we'll talk about later. Resistors are not in the exam. But resistors dissipate energy because they heat up. And then the energy goes into heating the resistor. A capacitor is not something that dissipates energy. Technically, it's just storing it in charge, and then the energy stays there, and then you can recover it to do whatever you want with it. So they're useful for that reason, and you would want to have high energy density. Now, we're not, in our case, for us right now, the main thing is not that. Of course, that's very important. That's, those are the characteristics of the capacitor. But for us, we don't want to have something that looks like that, because that's not a constant electric field. So that's kind of messy. We rather use capacitors where the field in between the plates looks almost constant, because then it's a little easier to handle. And so we're going to do that. Okay, we're going to use the one that people always use. In the end, they're doing that because they're assuming that it's an infinite plate, and then they're using an equation for the electric field that means the electric field is constant. So you shouldn't draw it like that. That's not a constant electric field. When the lines start to separate from one another, so constant electric fields have to be like this. There's not separating. The electric field lines are not separating. Here they're separating, so obviously that's not constant. So we're going to use most of the time, just for convenience, we're going to use the case of two plates. But again, anything can be a capacitor, really. But here we're going to do two plates. Now, the units of capacitance are farads. And the capacitor is defined in this way for reasons that have to do with the fact that when you define it this way, actually, this capacitance is just a property of the size of the plates. And there is a little bit of a derivation in a second. I could do it right now, but let's postpone that for a second. I'm thinking of what you need for the exam. So I want to make sure I get to that today. So you can start preparing for the exam. And then I may have to mop up a few things here and there, and I may save that for Monday. Okay, so the definition of a capacitance is the charge that the capacitor holds divided by the potential difference. Now, this is not potential energy. So again, this is potential. This has units of volts. We discussed that last time. There's potential energy that has units of joules. Energy is always joules, but this is not joules. This is volts. So it's the potential between the two plates. Okay, and we will see later on that when you have two plates, since the electric field is a constant, the potential difference between the two plates is ED. Now there's a negative sign in there, but let me not worry about the negative signs today, okay? Just make it easier. I'll again show you how to deal with signs in a second in a way that you don't have to keep trying to remember how the signs go. But because the electric field is a constant for the cases we're using, and we're going to use in the exam where you have two plates, the electric field inside is a constant. I'll repeat that in a second, okay? But so when we have, okay, let me repeat it right now. Let's try to get that straight. I did give you formulas for just one plate. The formula for the electric field for one plate was like this. Okay, this formula was the electric field due to one plate, so you're by itself. Okay, now a capacitor normally is two plates. Okay, I don't want to get into the Gauss's derivation of that right now because I will do that on Monday. But when you have two plates, not one, but two of opposite charge signs, so now you have two plates like this, which is what we're going to be dealing with here. You have a positive, and then you have a negative. That's the situation we're going to encounter most of the time when we're talking about capacitors, or almost always. Okay? When you have two plates, in that case, what ends up happening is the electric field outside the plates is zero, outside both plates. So here is zero, and here is zero. But in between the two plates, then the electric field is twice that value that I just wrote here. So what I wrote here, this formula does not apply. Okay, this formula is off by a factor of 2. What the field in between the plates, and this again, this is an assumption I'll show you. I'll derive it using Gauss's law, not today because that's a different topic, Gauss's law. I don't want to get into that right now. But I'll do that for you on Monday. If I forget to do it, please remind me. I'll try very hard to remember. That's something you should know how to do, yes. But the bottom line is when you use Gauss's law, what you find out is that when you have two plates, in between the plates, the electric field is given by this formula. Sigma, which is the charge per unit area, divided by epsilon, without the factor of 2. Okay? This factor of 2 is only one plate. And I'll show you how that works out Monday. But here, in between the plates is this value. Outside the plates is 0. No electric field. Basically, what's happening is that the electric field of the bottom plate cancels out the electric field of the top plate in the outer regions. In the in-between region, instead of canceling out, they add up. And that's what I'm going to show you Monday. But right now, let's just take it as a given. On Monday, I'll show you how the canceling happens and all of that. But right now, E equals 0, E equals 0. In between the plates, E of this much. Okay. Okay, so that's the electric field. Now remember, at the end of last class, I told you that, yeah, there is a relation between the electric field and the potential. One is the gradient of the other. Okay, in this situation, though, because the electric field is a constant, then the formula, only in this situation, okay, don't use this formula somewhere else. That happens a lot in this class. People know a formula, they want to use it. Of course, we've already been through a case like that when you want to use the formula for the potential energy of an individual charge and you apply it to plates. No, you got to be careful where this formula only works if the electric field is constant, as it is here. Okay? So this is fine for the constant electric field. Okay. So if you want to say this V is the voltage here. Okay. So actually, we could already derive something. When I get to it in the PowerPoint, I'll derive it. We already have the formulas to derive what the capacitance is because you can replace the voltage by ED. ED is the separation of the plates, the distance between one plane to another. So this would be D here. And then you would replace the sigma, the electric field, with the value for the electric field in between the plates. And then you would stick it in there. And then you would find out you could rewrite the charge Q in terms of the area of the plate. And then you could find out that actually the capacitance only depends on the properties of the plate. This formula is below. When we encounter it, I'll write it down for you. It's just what I just wrote. You can write it and then show that to be the case. Where is the formula? Okay, here we are. So let's do it right now then. Okay, so let me erase this. Let's do it right. So this is the formula I'm talking about. I didn't know it was right here, but it is. So let's do it again. I had done it before, but let's do it all over again. Okay, so I just told you that the voltage, I just said the voltage equals ED. I said E equals sigma over epsilon naught. We also know that sigma equals Q over A being the surface area of the plate. Therefore, we could write the electric field also as sigma, okay, well, let's write it as Q over A epsilon naught. Then I can stick the E in there. And then once I've done that, I can stick the voltage in there, and then I get this. That's the answer. So what is this formula telling you? It's just saying the capacitance, in the end, is a quantity that depends on the surface area of the plate. And that's something they have to give you. Whereas you have a plate, what is the surface area of the plate? So you see area of each plate and the distance between the plates, D. So all I did is I used this formula, which applies only when the electric field is constant. It is constant here. Then I plugged in the electric field due to two plates, which I just told you what it was. It was sigma over epsilon naught. And then I figure out what sigma was, which is Q over the area of the plate. And then I put it all in there and I get that. Okay, so the capacitance depends on the properties of the plate. It's not a variable. Okay, so that's why they define it this way, because it comes out to depend only on the properties of it doesn't depend on how much charge. The charge is canceled out because the charge was in the bottom here and the charge was also in the top there. So basically they're canceling out the charges, so it doesn't depend on the charge. This capacitance doesn't depend on the charge. Depends only on constants that are a property of the plates. And you of course want to have a big capacitance. That just means how much charge you're storing for a given voltage difference. So even with a small voltage difference, you can store a lot of charge in the plates. Well, yeah, that's a better capacitor. You want to store more charges, of course. Okay, all of that is pretty, those are just basically definitions at this point. Now, the one thing you should remember is the capacitance has units of farads. Okay, so, well, you can tell what units those are because it's charge, which is coulombs, and volts. So it's coulomb per volt. Okay. Okay, now let's not talk about, let's just go to the usually capacitors come in very small units. So it would be microfarads. Okay. Let's actually just get right to the already, since I know this is not going to be as easy as it seems at first. At first, it seems it's going to be pretty easy. Actually, it's not that easy to solve capacitors and figure out all the charges on all the capacitors. So let's not spend a lot of time on definitions of this, definitions of that. Let's just launch into the example that you really need to know how to handle. Okay, so I'll start a little simple. It's the same. We're going in the right direction now already. I don't want to talk a lot more about dielectrics or anything. So let's just launch right into the thing you need. And the thing you need is to figure out if I have a voltage across capacitors, what you really would like to know is what's going to happen overall. Okay, so let me show you why that might seem at first sight. I'm going to try to show you. Let me break off here and show you why, even though it seems like we've already given enough information, we haven't. Okay, let me tell you what I mean. Again, let me try to help you out. From here on out, I'm going to start helping you out already with the exam stuff. I'll come back to the PowerPoint in a second because it does have, I want to show you in the PowerPoint where it says about capacitors being in series, capacitors being in parallel, and the exam will have a bunch of capacitors in series and parallel, and then you want to say what are the charges on each capacitor. You could ask multiple questions. You could ask different kinds of questions. Sometimes in in Master in Physics, they will ask you questions that are very easy, but you could also ask questions that are not quite so easy. So I want to show you both kinds, the very easy ones and the ones that are not quite so easy, and then show you that that can happen, and you have to figure that you have to figure all of them out, actually, not just the easy ones, if you want a perfect score, or if you want to get it all. Okay. Okay, so let me start with the problem I was just in and ask you a question. Let's see. So we have a definition. We have already given a definition for a capacitor, right? So we say a capacitor is the charge divided by the voltage across the capacitor. Okay, so let's since we're going to have two capacitors, let's have variables here. So we have capacitor 1. We're going to do the exact same thing that was in the PowerPoint, but I'm going to present it slightly different, just to get you to think about this a little more, okay? Before just giving you answers, because then you forget the step later on if I just give you answers. So I'm going to have one capacitor, and that's going to be the charge in that capacitor, and the voltage across that capacitor. That's the value of the capacitor 1. And then I'm going to have a second capacitor. And we're going to be charge 2 divided by voltage 2. Okay, those are the two capacitors. Okay, so now the question is this. Now you put them in series, say. Series means, okay, we'll see what series means, but I'm going to draw what it means in this situation, like this. So I have capacitor 1 and then capacitor 2. And now I'm going to put a voltage here of whatever, you know, it doesn't matter what I do. So 10 volts, I don't know, whatever. 10 volts I'm going to put there. Now this is the same case that was in the PowerPoint, but I want to think of it from scratch without showing you answers. Okay, so if you were very fast to look at the PowerPoint, you might have already seen the answer, but I want to take a step at a time to see if we realize what the key step is to solve this kind of a problem. So now what they would tell you in the PowerPoint immediately is, of course, you have two capacitors, and each capacitor depends on the voltage across that capacitor. So V1 would be the voltage dropping going from there to there. That would be V1, the voltage 1. And then voltage 2 would be across from here to here. Well, of course, if you start here and you go all the way around and you come back to the same spot, you must have the same voltage. That's a rule we're going to apply a lot later on. If you go around the loop and you come back to the beginning, then you can make the voltage go up and then you can make the voltage go down. But when you're back to the same spot, you must be back to the same voltage. So you have a voltage difference of 10 when you go from this side to that side. Well, whatever that voltage difference is must be the same as the voltage difference across both capacitors, because that's one loop. So it's pretty easy to figure out that since voltage is something that you can check in the lab, you can always check this to see if it's true. And of course, it's always true that if you go around and you come back to the same, then the voltage sometimes goes up, sometimes goes down, but it comes back to the same value when you're back to the same, of course. So that all the voltages have to add up to 0 when you add all around the loop. Some are positive, some are negative, they add up to 0. Well, what that means in this situation, and we'll come back to that later, but of course it's always true. In this situation, what that means is that the voltage across the battery must, of course, equal the voltages across each of the capacitors added up. Okay? So there is a total voltage difference across both capacitors of 10, because that's what the battery is providing. Okay, again, we'll call this later on, we'll call it the loop rule. Okay, there is a formal name to it, but it happens all the time. You analyze all the circuits, you can analyze every circuit. We will start analyzing circuits in a different way by using these rules about parallel and series. But really, in the end, you will find out that there are other rules that you don't have to think whether something is in parallel or is in series. The parallel and series thing does help a little bit, makes things go faster sometimes, but you don't really have to do that, no. That you might want to do that just to go faster in the exam, sure. But there are other ways to solve circuits. Okay, anyway, so yes, the loop rule tells us that, of course, that when you go around the loop, the voltages must add up to 0. So one way to write that condition is to say 10 equal voltage 1 plus voltage 2. Great. Now, so we have one equation that always works. When you go around the loop, you always can get an equation like this. Now, what we would like to know is, the charges on all the capacitors. If you're going to know everything, you would like to know everything, right? So you know, this is something that is given. Okay, remember, I just showed you the equation went like this. The capacitance equals epsilon naught A over D. That was the equation. So that's something that applies to a capacitor. So once you know the surface area of the capacitor and you know the distance of the plates of the capacitor, and this is just a constant, then you will know the capacitance. So of course, in problems, they always give you the capacitance, 5 microfarads, whatever. Okay, so these two things in the lab, certainly, those are the things you know ahead of time. They actually give you a meter to measure those things, in case you don't trust the rating that's spelled out in the capacitor. Then they give you a meter to make sure the rating is correct. Okay, so the C1 and C2 are things you know. Great. Q1 and Q2, you don't know that. That depends. The 10 volts, if you change to 20 volts, well, the charges will change. Okay, so it seems that in this situation, it seems like you have, you want to know everything, and you have, so how many equations do we have? Let's see if this works out for us. Okay, so I'm trying to get, instead of giving you the answer, I'm trying to get you there without right away giving out the answer. Supposing this situation, seemingly I've given you everything you need. I give you 2 capacitors, say both 5. Say C1 equals 5 microfarads, sorry, not coulombs. C2 equals 3 microfarads. Okay, so this is the information you know, and then you know you have a 10 volt battery. And what you want to know is solve the circuit. Tell me everything about the circuit. So in order to tell you everything about the circuit, what do I need to know? Well, I need to know Q1, Q2, V1, and V2. So these things are unknowns. The Qs you don't know, and the voltages, you have this condition, but you don't know them individually ahead of time. Okay. So we have, therefore, we have 1 equation, 2 equations, 3 equations. How many unknowns do we have? In these three equations, how many unknowns do they have? What do you think? Again, I don't want to just give you the answer. This equation, we don't need this equation. I already gave you these values here, so that equation is not useful. That's when you would need to find out what the, so you're saying 4, right? Okay, so we have Q1, V1, Q2, V2. Those are 4 things you don't know. How many equations do we have? These are just values for those variables. But how many equations do we have to solve? We have 3 equations, right? 1, 2, 3. I mean, it's pretty simple. Now, at first sight, I don't want to give you the answer right away, because I want to just make you think a little bit about what's going on, just to help you remember. Maybe you won't figure it out right now, because you know, it involves a little bit of a conceptual point. But right now, it seems like we cannot get an answer, right? Because it seems like we're stuck. Now, maybe somebody has done this kind of problem already, and they know already what the answer is. But I want to make sure you do, and spend a little bit of time again, and then we'll get a little bit more complicated. How much time we have left? 45 minutes. It should be okay. As long as we concentrate on the practical things, then we'll be okay. Okay, so it seems like we have 3 equations and 4 unknowns. So it doesn't seem like we can get an answer. When you have 3 equations, but there are 4 things you don't know, how are you gonna find an answer? It doesn't seem possible, right? You need, for 4 unknowns, you need 4 equations. Otherwise, you're not gonna be able to solve for everything. So what's going on? Does anybody know the answer to that? So the question is, how do I find all information about this circuit? This is a circuit you could build in the lab. So how do I find out the information for this circuit? Yes, of course, it's AS. We can, of course, but you can do whatever you want. But again, you have 3 equations and 4 unknowns. Let me give you an example of what I mean by that. Suppose I want to tell, forget this equation. So suppose I have 1 equation and 2 unknowns. A1 equals 3A3 plus 10. And then I say to you, I have 1 equation, 2 unknowns. I'm making it simple. And I say, oh, okay, solve for A1 and A3. How are you going to do that? You have more unknowns than you have equations. That's not going to work. Right? It doesn't matter. You could do this, you could do that, you could move it around. It won't matter. If you have more unknowns than equations, you will not be able to find the answer. It's the same thing as what I just wrote. If I give you 1 equation, the one I wrote at the bottom here, and I say find A1 and A3, you can move things around. It makes no difference. You can't find 2 unknowns with 1 equation. Can't do it. Okay, so this applies in general. In order to solve all the unknowns, you need an equal number of equations. And the equations also have to be independent, by the way, but we'll get to that later. That's not really a major point right now. But so far, we only wrote 3 equations. So you can try it if you want. You're not going to get an answer because you don't have enough equations. So what's going on? Obviously, you should be able to figure this out. Okay, now you're going back to the rule that we haven't learned yet about what happens when 2 capacitors are in series, right? That's right, Karen, but that's kind of cheating because in a way it's like saying, it's not cheating, really. You can always go to a book and find the answer and that would help you, what you're saying. But the thing is, well, how did they get that equation for the total capacitance in the first place? Of course, I could go to a book and get the equation for the total capacitance of a series. These are capacitors in series. Okay, why? Because they're in series because their voltages add up. I'll talk more about the parallel case, but this is in series. Okay, so you put 1, then you connect the next one. We'll come back to the PowerPoint and you'll see that there's series and there's parallel. So you can talking about it. Okay, so let me tell you what the conceptual. This is not something that occurs to you right away. But I'm telling you, somebody had to figure it out in order to make progress. Okay, so when you have a situation like this, what's happening? So obviously, we have too many unknowns here. We have to lower the number of unknowns somehow. So this is important because you got to keep it in mind when I'm going to ask you to solve the charges of all the capacitors in a circuit and put what are the charges of everything. So you need to know, okay, well, how many things do I really need to know then if I do that? Okay, so let me tell you something that's very important for capacitors in series. And this you will see later in the PowerPoint that they're doing the same thing. I'm not making this up. What you're saying here is say, okay, if I put Q1 here, so what do I mean by that? Q1. So let me put well, this side is positive, right? And this side is negative. So this side of the capacitor will be positive charge on this side. So therefore, this side will be negative, and that's what creates the potential drop. You go from higher to lower. Because the bigger side in the battery, that's the positive side. Okay, so you're going from plus to minus. Now, how much? So you're saying Q1. Okay, great. Now, there is negative charge here. So what you have to ask yourself is, where did that charge come from? Okay, this piece of this plate here is not connected to anything except this other plate, right? And we know there's conservation of charges implicit throughout the class. Actually, there's lots of equations along the way. All comes down to the same thing. The charges always come from somewhere. They don't appear out of nowhere. Okay, it could come from a battery, it could come from a plate in a capacitor, it could come from wherever. If you have a junction, the charges don't disappear. Either they go that way or they go that way. So in this case, what that condition is telling you is that the charges on this plate came from this plate. So therefore, you don't have two charges, Q1 and Q2. It turns out you only have one. So it's Q1 equals Q2 equals Q. So you would have to put a Q1 there and a Q1 here, which is negative. Okay? This is always true in series. This is how it works. So the charges, the negative charges that are over here, they had to come from this plate because that's the only thing it's hooked up to. So in series, the charges of the plates must be the same. So this is true in series. Always true in series. It has to be true. You have two capacitors in series, this is true. Okay. Now, so I'm just giving you the conditions. We're going to see the same conditions in a second. I'm just giving them to you in a different way than in the PowerPoint. Okay, just you'll see that the same thing applies to the PowerPoint though. I'm just stating them in a different way. So Q1 is now for parallel. For parallel here is the same thing, but in parallel. Well, I mean the same sort of argument. And here I put a battery. And the battery I'm going to make 10 volts. So what is the same when these two capacitors are now in parallel? Okay? And the question is, what is the same in parallel? So what's before in series is the charges on both capacitors must be the same. That's very important to know because when you have a bunch of capacitors that are in series, you don't want to keep looking for more and more things. If you know that they all have the same charge, then you're not going to find the charge of the next and the charge of the next. You already know it. They're in series. It's the same charge on all of them. Okay. When they're in parallel, it's not the same charge. Charges are different. So Q1, so let me spell that out in case anybody, so you might want to write this down to make sure you got it because implicitly people don't spell it out like this, but yeah, of course, they're always using this. So for the parallel case, Q1 is not the same as Q2, of course not. You put a charge here, the charge can be different. What's the same in this case is the voltages. So V1 equals V2 equals V, which equals 10 in this case. So for parallel, the voltages are the same across both capacitors. This is always true. Okay? Okay, so now I'm going to go back to the PowerPoint, then I'm going to give you a case. And that will take us the entire class for sure, because the case is, again, actually, by the way, the case I'm going to do is right out of the practice exam. It's already on the PowerPoint. Just look for practice exams. You'll see it in there. So it has the answers as well. So we'll get this started. I'll get you thinking about it, and then you can always check the answers from the practice exam to make sure you got it. Okay. So let's go back up here though and give the answer to my dilemma here. It's like I said, well, we have 3 equations, but we have 4 unknowns. Well, actually, no, you don't have 4 unknowns. You only have 3 unknowns because Q1 equals Q2. So those 2 are not different unknowns. They're the same unknown. So the actual unknowns are Q, V1, and V2. These are the things you don't know. It's the same Q. Okay, so we don't need to put Q1 and we don't need to put Q2. We can just erase that. So we erase the 1 here and erase the 2 there. So we put a Q and then you put a Q over V2. So now you have 3 unknowns and 3 equations. So of course you can solve that. That's not a problem. 3 unknowns and 3 equations is fine. And now you know the charges. Now you know the voltages across each. You have 3 unknowns and 3 equations. That's perfectly fine. You can always solve that. Okay, now let me go back to the PowerPoint and then I'll do it just to show you it's the same thing in there. But I will write the series and parallel cases. But always keep in mind, in series, this is always true. And in parallel, this is always true. V1 equals V2 equals V. The voltage across both So why is that? Well, it's kind of pretty clear why that is for this case. Let me just say one more comment, then go back to the PowerPoint. If you can use a wire to go from one place to another without encountering anything, a wire just means constant voltage. So the voltage here, I can go from here all the way here. So the voltage here and here must be the same because there's a wire connecting them. And there's no resistors in between, there's nothing there. So if I can go from there all the way there, so the voltage on one side is the same, but the other side must also be the same because there is a wire that connects them. So the voltage is the same on both sides. So of course, V1 equals V2 equals V. Okay. Hopefully that's pretty clear. Let's go back now to this and show you that that's exactly the same thing they're writing here. Right? They're writing, they have a voltage difference. This is the battery. We put a battery there. And they're telling you that they didn't write Q1 and Q2. They already assumed Q1 equals Q2 equals Q. That's right in the drawing. So that happens because, you see, they just told you that here. So it's very important to realize that. Otherwise, you find yourself in situations where you don't know what to do anymore because you've added too many variables in there and you're not coming up with enough equations and then you're stuck. But you always have to remember that you can always do this. Whenever they're in series, you can always just keep one charge. Just keep the same charges on both. And then they have this condition, which is the same thing I wrote. 10 equals V1 plus V2. Okay, so it's the same thing. Okay, great. So now based on that, it's not that difficult to derive, but again, I want to keep it practical because I can tell already I'm going to run out of time, so I don't want to derive things, even though it's kind of easy. You just use let me tell you how you would do it. You would just use the potential rule, the V1 equals V2, then you will replace each V by the capacitance. So remember that C, okay, let me do it quickly here. V1, like what I was doing before, V1 plus V2 equals V total. V1 is across one capacitor, V2. Okay, well, but we have C equals Q over V. So I can solve for V and I will get V equals Q over C. So where it says V1, I can put one capacitor. So what would that come out to? Well, it's 1 Q. So I would put Q. And then I would put over C. Okay? And that's C1 because I replaced, and now I would do the same here, Q over C2. And then here I would write Q over C total, the total capacitance. The Q's cancel out. Why? Because they're the same. And then immediately I get this equation. Okay, so again, if you did, I went too fast through the derivation. There are 3 terms. You're replacing voltages with capacitances. And immediately you get this equation. Is the capacitance is the inverse of the voltage. That's why it shows up at the bottom. Okay, anyway, let's just get to the equation is fine. You can use it. You can write it down. Let's get to using the equation. What are they trying to tell you with this equation? Okay, so what they're trying to tell you is that if you want, what you can do when you have, you don't have to do this, okay, if you want a little faster, what you can do is whenever you find capacitors in series, 2 capacitors in series, you can replace that capacitor by just 1 with an equivalent capacitance given by this. Now, please, I noticed that many times what people do with this is they just do 1 over C, and they forget that this is 1 over C as well. So they just add up 1 over C plus 1 over C, and they think that's the capacitance. That doesn't have the right units. Okay, so you got to do 1 over C. People write it in other ways as well. So, you know, please, okay, so you could also write it like this if you wanted. Okay, you can also write it like that, but remember that I inverted the whole thing to get this equation. So you have to write it however you want. But if you want to find the equivalent capacitance, you can do this. You can take one capacitor and the other capacitor and apply this formula. The bottom formula too was better, faster, the bottom formula than the top formula for sure. Notice that to get this formula, I already inverted the formula because it's 1 over C equivalent, not C equivalent. So anyway, I inverted everything. I did it all for you. There is the formula. You can use it if you want. So if I know one capacitor and then the other capacitor and they're in series, then I can replace that with only one with this capacitance. Okay, there's no problem with that. That's fine. But you will see that this doesn't always give you the answers you need. You can, of course, do this. So this would be 4 plates in series, capacitors in series. This in general, you add more capacitors, all of them in series, then you keep adding the voltages, and then you will get something that looks just the same. The Q's keep canceling out. The Q's are always, so again, if you have 10 capacitors in series, they're all in series. One capacitor, join, another capacitor, join, another capacitor. All 10 of them will have the same charge. Okay? In series, they always have the same charge. So I can replace all 10 of them with one whose capacitance is given by this expression. However many you want to put in series, it makes no difference. Okay, this is for series capacitor. They always have the same charge. Great. In parallel, the charges are not the same. You see, they already have Q1 and then they have Q2. What's the same is the voltages. So they don't do V1 and V2. They only have one V now. And this is V. So because it's the same. So what changes now is the charge of each capacitor is different. But the voltage is the same now. Okay, so let's go right to the practical example, but let me close with a rule for parallel capacitors.
Professor?
Yeah, please, go ahead.
Can you just go to the previous slide just for a minute?
Sure, of course.
Yeah, just wanted to...
Yeah, write down what's in here, yes.
Okay.
Right, so you can see what I was saying is that the voltages are the same in this case, right? They don't have V1 and V2. You just have V. Because they're the same, and V is the same as whatever this is the battery gives you. But in this case, you have 2 different charges for each. So if I ask you, if in the exam I ask you, tell me the charges on all the capacitors. Well, if they're in parallel, then you gotta find the charge on here and also the charge on there, and it will be different charges. But if it's in series, it's only one charge. If you find one of the capacitors, then you know the other. Okay, now there is also the rule for parallel capacitors. Okay, so here they give it to you. Now they have to tell you the total charge now. When you replace the capacitor, before they didn't have to tell you. So you have, because it's the same charge. But here they have to tell you, okay, when you replace 2 in parallel, 2 capacitors by 1, then it is as though you had one capacitor with charge which is the sum of the 2, and the capacitance which is the sum of the 2. Okay? Okay, so you can of course replace parallel by using this rule. You can start, okay, so let's do practical examples of this. Okay, I'll start very simple, but then again, I'm telling you that there will be a moment when to get all the information, it can get a little bit confusing. So I'll start simple just to show you. So let me just go, I'm gonna go to things just like in, let's start simple, okay? Let's go, again, I'm gonna do, this is from the practice exam at this point. So already I'm on something that's very similar to what's gonna show up that is very similar to what's going to show up in the exam. Okay, so let's start just by making it super simple. Let's make it as simple as possible, you know, and use ones and so on. So it's very easy to figure out what we just did. So if I have 1 microfarad and I have 1 microfarad, I always have that trouble when I'm writing at the top. 1 microfarad. Then I want to know what is the equivalent capacitance of this thing, so I can replace it by just one capacitor. So since I already said what the rule is, just to make sure we're on the page, what is the equivalent capacitance? What is the capacity? I'm replacing 2 by 1, right? What should I write for this? What is the capacitance of that thing? Go ahead. I mean, I already gave you enough info at this point that you can answer this. So I'm replacing 2, which are in parallel, with 1, which is equivalent to 2 in parallel. So what should I say the capacitance of this thing is? We just gave the rule. So you said 0.5. Sorry, this absolutely. Sorry, this is in series. Absolutely. So this is where the charges are the same. Okay, so you're still sticking with a 0.5, right? Everybody agree? Let's make sure we got it. Okay, so it would be 1 over C equivalent. Again, let me make sure, because people I know they forget to invert the 1 over C equivalent. Equals 1 over 1 plus 1 over 1 microfarads. Let's forget the microfarad part. That doesn't make any difference. So you say 1 over C equivalent equal 2. So C equivalent equals 1/2. I'm just spelling out how he got that. Emma, Yeah, okay. It's 1/2. Let me use the other formula I wrote. You might like that one better. Okay, I don't know. That's up to you. This is fine, but you gotta remember to invert. There's nothing wrong with it, but you gotta remember to invert. But the other formula I gave you is this: is C1 times C2 divided by C1 plus C2. What does that give you? It gives you 1 times 1 is 1, 1 plus 1 is 2, so it gives you 1/2. So in that case, because the way I wrote it, you don't have to invert anymore. It's already inverted. So this might go faster. It's up to you what you want to use. This is fine. It's easier to remember. This goes faster, in my opinion. Okay, so it's 1/2. Okay, great. So that's fine. So now start to add up more elements. So let's do this. Now, actually, I'm going to use one. Okay, yeah, I see the one we're going to have to do that's a little harder from the exam, and then we're going to try to get there. But first, again, there are different questions you can ask about this, but we're going to start from the easy question because otherwise we'll run out of time anyway. But also the numbers are a little different than what's in the. I'll put the same numbers as in the review in the practice problem. But let's start with this, and let's check again to keep it super simple. You know, you can put 100 volts, whatever you want, across the whole thing. That's the example from. It has 100 volts across this thing. That's the example. Also, it has 20 microfarads, 12, whatever, blah, 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 blah. Let's just do 1, 1, 1, 1, 1, just to go faster. For now, you know, in the exam, you had to do a little better than that. But right now, we're just going to put 1 on everything. Just make it go faster. Okay, so how do you break this down? Well, these two guys are in series. So we can use the rule we just did. There's a 1 and a 1 in series. So I can replace those two, which are in series, with another one by itself, which has 1/2 microfarads, right? The two of them becomes 1/2. So notice one thing in particular. It's good to remember this. When you have them in series, the equivalent capacitance is always less than either one of the capacitors you have. Always less. Okay, so 1/2 is less than 1 and 1. Okay, so the equivalent in series is always less than the capacitors you start out with. Okay, so this is 1/2. Well, the bottom is also 1/2 because it's the same thing. Okay, now you have now you're reducing. People call this reducing the circuit. So basically, at this point, since I've already replaced all those things, then I have this. I can think of this circuit instead. 1, and then I have 1/2. And again, just to go faster, let me drop the microfarads. Of course, it should be microfarads for everything. 1/2 and 100. Okay. Now you could say, okay, this is in series with this, but that's not 1, that's 2. So you don't want to do that. You want to, whatever you know immediately what it is, you do that. So this one here and that one there, those two are in parallel. So what do you do in parallel? How do I replace these two here on the right? You just add them, right? So it's very quick because parallel is very easy. When they're in parallel, you just keep adding. How do I know they're in parallel again? Well, isn't the voltage across both of them the same? The voltage here is the same as the voltage here. The voltage on this side is the same as the voltage in that side. So of course they're in parallel because the voltages across on both sides are exactly the same. They have to be in parallel. Okay, that's what the wire buys you. It tells you that the voltage must be the same. Okay, so you just add them as Karen just said. So you have 1. And then you have 1 because it's 1/2 plus 1/2. Okay, great. And then 100 volts here. Great. Now one final step and we're done. Now these two now are in series. So now you do the series rule again. So the whole thing goes like this. 1/2 Okay, great. Awesome. So what did I just found? I found the equivalent capacitance of the circuit, of the entire circuit. Right? I found the equivalent. If I want to replace all these capacitors with one capacitor, then this is it. It's a 1/2 microfarad capacitor. That's the equivalent of all the other ones. So if somebody is telling you what is the equivalent capacitance of this circuit, and if you clearly can identify parallel, then series, parallel, series, so on, you just keep reducing the thing until you're down to one capacitor, and that's the eventual equivalent capacitance of that entire circuit. That's great, except this doesn't give you all the information. So this seems pretty simple. I think we can agree that it didn't take us that long to do it. If you put numbers in there, well, you have to be a little careful with the calculations, make sure you don't make any mistakes. But you could always do the same thing, keep doing it, and then find a final number for the equivalent capacitance of the circuit. The problem with this is that it gives you a little bit of a false sense that, oh, I got it, it's not that hard. And this is why. There's a little bit more thinking to do here to get it completely, because this only gives you the final equivalent capacitance. But suppose I ask you this, and let's see if you can do this on your own instead of me telling you how you would do this. But suppose I tell you this, tell me the charge of this capacitor. That's my question. My question is not tell me the equivalent capacitance of the whole thing. I want to know what charge is going to be when you hook it up. I want to know ahead of time what is the charge on just this capacitor, not the charge somewhere else. I'm interested in the charge on that capacitor. How would you do that from here? Okay, let's start with the charge in this capacitor first. How would I get the charge on here of the equivalent capacitance? How would I get that? We have to eventually get back to what is the charge on this capacitor here. But let's start simpler than that and say, okay, you have this equivalent capacitance here, and I want to know what is the charge on this equivalent capacitor. How would I find that? Yeah, just that, right? So that's just the definition of what a capacitor is, right? So I would say C equals Q over V. Now I know C, what I'm looking for is actually Q, right? So as Manderjit said, you find Q is just CV. So it has a voltage. Well, I know V is 100. I know C is 1/2 microfarads. So I multiply those two. That's it. That's the charge. Okay, fine. That's true. No problem. Okay, so let's go backwards now. Okay, let's work backwards. So now what is the charge? So this is the charge on this equivalent capacitance that I just replaced the entire circuit with. I just calculated it, equals 100. So it's, okay, let me in fact do it, 0.5, right? Times 10 to the negative 6 times 100 volts. Okay, so it's 0.5 times 10 to the negative 4 coulombs, or 5 times 10 to the negative 5 coulombs, right? Okay, so that's how much this tells me it is. Now, how much is the charge on this capacitor? We're walking backwards. That's what you have to do. So now we got a number for the charge on this capacitor at the end. What is the charge on this capacitor? What is the charge on that capacitor? We're going backwards from the thing we were doing. We'll keep decomposing, reducing. Now we're going to go backwards, see if we can figure out what the charge on one of the initial capacitors was. So we already found out what the charge is here. How about the charge on either one of these? What do you think? We're here now. Right there. Okay, same as what? Yes, the same as each other, and equal to what value? Equal to this value. Right. Correct. Okay. But you see, it's going to get a little tricky because in series, you got to keep remembering that they're in series. Oh, so that's what that means. So in series means that if I want to know what the charges are on each of these two, that would be the same. So wow, notice one thing. You already know the charge on the original capacitor for this side because you just calculated it. It's 5 times 10 to the negative 5 coulombs. That's already one of the initial capacitors, not a reduced equivalent capacitor, the original capacitor. Okay, how about this one? We just said that one is the same, 5 times 10 to the negative, because they're in series. These two are in series. Okay, great. Now we'll go backwards once more. So how about this one and this one? We're at 5 times 10 to the negative 5 coulombs. But now we're going back and we have to get this one. Correct. Now, I picked an example that was a little easier because what you're saying is exactly correct. So what is Ilbron saying? That, okay, when they're in parallel, they add up. So they have to add, and they're both the same. Since they're both the same and they add up to 5 times 10 to the negative 5, then each one is half that value. Right? So you couldn't write 5 times 10 to the negative 5. That would be wrong at that point. For these two, you have to say 1/2 of that, so 2.5 times 10 to the negative 5. Okay? Okay, let's give a little bit more difficult example. Okay, let's the one kind of like the one that's going to show up in the exam. It's kind of like you're doing the same thing. There's a step here that if the top is not the same as the bottom, here on the right side in parallel, both sides up, the upper one and the lower one had the same value, 1/2. That's why it's half the charge, as Ilbron said. But if they're not the same value, you have to be a little bit more careful still and try to figure out what is the charge is different on each one, because they don't have, it's not the same capacitance. So let's go back. Let's do a practical example. And again, it seems like I'm going to run out of time. This class is over at 2:45. But again, this is from the practice exam, and I'm not gonna just ask you what's in the practice exam. Actually, what's in the practice exam is pretty good already, actually. Yeah, it's pretty good. So let's set it up. Let's do the same. So we're all with the same numbers and so on. I'm gonna do the same case as in the practice exam. So the first question is, here's the circuit, and it's 20 microfarads, and then 12. So we'll get started, but we won't finish. But the first question you would ask is, again, what is the equivalent capacitance of the circuit? And that's the question in the, so there's 12. And then the other one is 12 again. Okay, and then there's 100 volts across this thing. Okay, so first question, what is the C equivalent? Okay, so go ahead and find it. See if you can find it. I mean, you don't have that much time. You only have 5 minutes. But just to push yourselves a little bit, try to get it right now. See if you can do it in 5 minutes. You don't want to waste a lot of time doing this in the exam time. So the first part of the equivalent capacitance of the whole thing, you should be able to get pretty quickly, not wasting any time. See if you can do it. You have 5 minutes. See if somebody gives it to me in 5 minutes. Again, the answers are, they're on Canvas, but it would be better if you didn't look and just give it a try, see if you can get it, just to test yourselves, make sure that you know how to do it. So I have the answer in front of me. I got it from Canvas, so I certainly can tell you what it is. Let's see if somebody can do it without looking it up, please, just for your own practice here. Okay, great. Very fast. Okay, you rounded a little bit too much. Let's just keep 2 significant figures. Also, to make it easier, you know why we should keep 2 significant figures? It helps me if you keep 2, because if you get the number right away that is correct, it's hard to get the correct number without doing the right thing. So it makes it a lot easier when I'm grading you, that I see you got the right number. And unless you're doing something totally wildly off the mark, I'm gonna think that you were doing the right thing and try to give you the full credit. So if you start rounding too much, you kind of make it harder on me to figure out if you were getting the right number. So just 2 significant figures works for me when I'm grading the exam. Just keep 2. Don't round it too much to 1. That makes it a little harder for me then to figure out you did the right thing. Yeah, it's no big deal. I'm not telling right now. I'm just saying for the exam, just like Elbron had the right answer in there. It's 8.2. She had the right answer. Or he, sorry. I got you. What? No. That's the right number. Okay, it's 8.2. That's the answer is in the practice exams. It's 8.2. If somebody writes 8.2, already I'm gonna think, oh, okay, great, they know what they're getting. Don't know, but the answers are on Canvas. We're running out of time, but the answers are on Canvas, so you can see. But it is 8.2. Okay, good. So you see why 2 significant figures help me, because it's just 8, and we don't know. But 8.2, I know I got it right. Okay. So please keep choosing and don't write more because that doesn't really make any difference. But two is okay, just to help me out. Microfarads. Yeah, it's microfarads. Also, it's microfarads. So in the end, you don't have to put it everywhere, but in the end, when you get the answer, you should give the right units. Okay, you add 8.2 times 10 to the negative 6 farads, or 8.2 times microfarads, or whatever you like. Okay, that's fine. So again, that part, notice, it wrote very quickly. Awesome, that's going to help in the exam for sure. Okay. You don't want to take forever to run that part. That's kind of like the easy part. So let me tell you what the hard part is again. The hard part really is, what is the charge there? That's harder. Right, because that's part you actually have to think about how to get that. The other part is just kind of like, I know. But when you say what is the charge there, and there's a little bit of thinking involved. Now, if you don't run out of time, so I'm going to have to continue next time. I'm still thinking that we're going to be able to have the exam by right date. But it's possible that when we want to practice a little more and I have delay in one day, I'll ask you guys what you think about that, if you get ready or not. I may have to delay one day. I'll try very hard. We're not done with this yet. I mean, I think we should be able to, let's try to do the exam. That would be a week from today, Monday. Yeah, let's I think we're gonna do it. So let's stick to the plan, not change it again. And so we have one day, and I'll give you, I'll remind you of the questions, and we'll do more practice exams. Basically, I have to finish out a little bit about this capacitors. I have to show you how to get the electric fields inside the capacitor, again, using Gauss's law. We have to finish it out. You can actually help me by going already to practice exams with Canvas and trying to come up with what is the charge on this capacitor. Okay. Try to find out how we can know that. I will give you all the information you need, but actually in practice, you got to think a little bit about that. So in the exam, you will need not only the overall equivalent capacitance of a circuit, that's one piece, but also that you should be able to get the charge on everything. So there's the charge on the 20, on the 12, on the 24, on the other 12, on the 2, any of the capacitors. Okay, and if you did that, then all you're going to do is there's nothing else I can ask you. You've already gotten answers for everything. Okay. So that's it for today. So I'll see you next time. Let's try again. Start working on our practice exam, and then we'll finish it up on Monday. But basically, we're actually done with the material pretty much. So it's okay. We should be okay. Yes. Okay. So 1 week from today, the exam. Okay. So that's it.